All right, welcome back, everybody. So today we're going to continue with our discussion on ways in which the singular value decomposition and relatedly eigendecompositions are showing up in various machine learning contexts. And to start, we're going to talk about PageRank, which is a method for determining the importance of different web pages, say in the internet, so that when you search for a topic, the ordering of the pages that are returned to you is prioritizing pages that are more important in some sense. So what do we mean by important? So what we're going to do is imagine that we are surfing the internet by just randomly clicking links. So I'm at some website and I just choose one of the links on that website at random and I click on it. Then there's a whole bunch of links on that website. I choose one of them at random and I click on it. And I keep repeating this process. So if I keep on doing this forever, then in some sense we will visit more important websites more frequently. Right, so if I have in my internet a huge number of sites that all link to Amazon, then as I do my random surfing, then I will hit Amazon more and more often. And so in particular, if we do this long enough, then eventually we will hit some sort of steady state. And in this steady state, you're going to have some new variable pi now, where pi I for my ith website is going to be the probability that we are at website I at any given time. Okay, so we start off by just doing this random surfing, and if we do this random surfing for an infinite amount of time, then at some point we will just, on average, be hitting site 1 with probability pi 1 and site 2 with probability pi 2, etc. And so then we can think of these probabilities as being a measure of this importance notion that we've talked about, and we can use that to rank different websites that perhaps match a search term or something. So let's think about an example of this. Okay, so we're going to create a little miniature internet here with 4 different sites, 1, 2, 3, and 4. And then we are going to think about what links are in this site. So in particular, if we think about which sites are linking to page 1, we are going to have sites 2, 3, and 4 all link to site 1. And then if we think about who's linking to site 2, we have sites 3 and 4 pointing to site 2. If we think about who's linking to site 3, it's only site 1. And if we think about who is linking to site 4, it is sites 1 and 3. Okay, so this is a graphical representation of our miniature internet, indicating which nodes are connected to which other nodes. And so these are our hyperlinks, and these are our websites. And so now what we can do is we can represent the structure of this network using a matrix. So in particular, we're going to let M be the adjacency matrix. for the network. And in particular, if we were to look at the ijth entry of this matrix, it's either going to be 1 or 0, and it's going to be 1 if site j links to site I, and 0 otherwise. So for our little example now, we're going to form a matrix, and we're going to say, all right, for the first row, which sites are linking to site 1? And that's everybody, sites 2, 3, and 4. And then if we look and we say, who is linking to site 2? We have sites 3 and 4. If we look and we see who is linking to site 3, it is only site 1. And if we say who is linking to site 4, it is sites 1 and 3. Like this. Okay, so this is our adjacency matrix. If you've got this graphical description of your network, then you can figure out what the adjacency matrix is. And once you've got the adjacency matrix, you can figure out what that network structure is. So this is just simply a matrix representation of exactly that representation on the board. Next, what we are going to do is we are going to divide each column by its sum in order to get a normalized form of this matrix. So we're going to call that new matrix A. So if we look at the first column of M, its sum is 2. And so the first column of A is going to be 0, 0, 1 half, 1 half. For the second column, we'll just have 1, 0, 0, 0. For the third column, we have a third, 0, and a third. And for the fourth column, we have 1 half, 0, and 0. Okay, so same information again. We've just done a particular normalization here. And this normalization is going to turn out to be extremely helpful to us. Okay, so in particular, what we are going to do is we are going to let our vector pi be equal to the vector of all of the different probabilities for all the different nodes in our network. So we're going to have pi 1, pi 2, all the way to pi n, if I've got n nodes in the network. And then I'm going to put a little transpose here because I'm thinking about this as a column vector. So this is the vector of probabilities or importances that ultimately I'm trying to calculate. And I'm going to use these adjacency matrices in order to do it. So in particular, we could imagine having a pi k that corresponds to the how often or how frequently we've visited sites after doing this process of random surfing k different times. Oops. Okay, so this top one is the steady state that we are going after, that we ultimately want to calculate. And when I have this k superscript, what we're saying is these are sort of like our frequencies of visiting the different sites after k hops, or after clicking on k different links. And so now what we're interested in is what happens if I keep up doing this random surfing forever. So what happens as k goes to infinity? So in particular, this pi k is going to approach this vector pi that we actually want to compute. But what I mean when I'm asking this question about what happens as k goes to infinity is how is this adjacency matrix that we've been talking about going to affect it? So if I'm at these different websites, each one with some probability, and then I were to choose one of the links at random then what are the probabilities that I'm going to be at any individual website in the next step? So my vector of probabilities or frequencies at the k+1th step is going to correspond to taking this vector at the kth step and multiplying it by this matrix A, normalized adjacency matrix. So what I'm doing here is I'm saying, okay, at time k, I've got some probability that I'm at each of the different websites. A is telling me something about the probability of going to each one of the different websites from there, right? So if I'm at website 4 over here, then there's only 2 places I can go from there, either to site 1 or to site 2. And since I'm choosing links randomly, there's a 50-50 chance of me going to one or the other. And so when I write this equation here, what I'm reflecting is the fact that I've got some probability of being at each one of the different websites, and then some probability of clicking each of the links at those different websites, and that's going to update my probability vector. And so then, as k goes to infinity, what I'm going to have, when I talk about this steady state, is that this vector pi is equal to this adjacency matrix A times pi. So my problem now is the following. Given this matrix A, what is pi? What is this vector of probabilities? And we don't want to figure that out by actually doing this experiment of randomly surfing the internet forever. That's computationally intense, and it turns out that just using a little bit of math, we can actually figure out what pi is without doing this random surfing. So in particular, when you look at this equation here, what does this look like to you? What does this remind you of that we've talked about in this class? Right, this is an eigenvalue equation. So recall that we could have a scalar lambda and a vector v, and they are an eigenvalue, eigenvector pair. For a matrix A, if A times the eigenvector is equal to lambda times the eigenvector. And so, with this equation that we've got here in terms of pi, this is telling us that pi is an eigenvector of A, and the corresponding eigenvalue, lambda, would be equal to 1. Okay, so let's flesh this out a little bit more. So in particular, we did this normalization for A. So A, in this context, is what's called a Markov matrix. All of the entries are non-negative, and the columns are all summing to 1, like vectors of probabilities. And Markov matrices have an important property where the leading eigenvalue lambda is equal to 1, and let's say lambda 1 here, and all of the remaining eigenvalues are smaller. So if we looked at all the different eigenvalues of A, lambda 1 is going to be equal to 1, and it's going to be bigger than lambda 2 and lambda 3 and any other eigenvalues that we might have. So not only is pi one of the eigenvectors of A, but in fact is the leading eigenvector of A, the eigenvector corresponding to the largest eigenvalue, which in this case is equal to 1. And so now all we need to do is to calculate what that eigenvector is. All right, so to do this, you could use a full just eigendecomposition of the matrix A. For something like ranking all of the sites on the internet, where the number of sites could be in the millions or billions, doing a full eigendecomposition can be very slow. So what we want to do is to just compute that first eigenvector in order to be as efficient as we can be. So I'm first going to show you a generic method for computing eigenvectors. And then I'm going to talk about a specialization of that to this PageRank setting when we have a Markov matrix. Okay, so for the generic power iteration method, we're going to have some pi1 be an initial guess. For pi. So we start off with some initial guess, and then we are going to iterate as follows. So for k equals 2, 3, 4, etc. What we are going to do is we are going to take our current guess, I guess we are starting at 1, pi k, and then we are going to multiply it by the matrix for which we want to compute eigenvalues, A. Here, maybe I'll do it like this, just to be -1. And then, in most power iteration methods, we normalize this because we are looking for eigenvectors with norm 1 typically. So we would divide by A times pi k minus 1. It's 2 norm. And so this normalized vector is what we are going to call pi k. And then finally, sorry, this is a little messy, but if my estimate pi k and estimate pi k minus 1, if it stops changing, if we are no longer making any progress, we say we're converged and we stop. But that's it. It's a very simple method where we're just continually, in every iteration, applying the matrix A in order to update our vector of probabilities. Very powerful and very effective. Okay, now, at the same time, when we think about PageRank, this might feel a little bit weird because what we are doing with this normalization here is ensuring that the final vector that we get has a norm, a 2 norm, that's equal to 1. But what I told you earlier is that in the context of PageRank, we want to interpret pi as being a vector of probabilities, right? Hopefully that will add up to 1 like most probabilities do. And so we would actually do something a little bit different in the context of PageRank to account for the fact that we're dealing with vectors of probabilities and Markov matrices. And so what does this look like? So with, okay. So for PageRank, let's initialize with a vector pi where all of the entries add up to 1. And then what we're going to do is try to ensure that that is true for every iteration. So we want this to be a vector of probabilities so that if I were to look at the sum of all of its entries from j equals 1 to n of pi j, and I'm doing this at, say, my kth iteration, that that is equal to 1. And now what I want to note, if my vector is a bunch of numbers that add up to 1, that are all non-negative, then if I just look at pi k plus 1, where I compute the product of the matrix A times pi k, and I don't do any additional normalization, then I will have that the sum of the entries of my new vector, pi k plus 1, also add up to 1. So if I start off initially with a vector of probabilities that add up to 1, and at every iteration, I don't do any additional normalization. I just take my vector and multiply by A, where A is a Markov matrix. Then, at each iteration, I will still have a vector of probabilities that add up to 1. And we can see this very clearly by just using the way that we specified this Markov matrix. So in particular, let's look at the sum from j equals 1 to n of pi k plus 1 j. So now what I'm going to do is I'm going to put in here that this pi k plus 1 corresponds to taking the sum from I equals 1 to n of a ji times my previous estimate, pi k, and its ith entry. And then I'm going to sum up the results of those operations. So each of these sums in yellow is giving me pi j k. Now what I can do is I can simply change the order of my sums here. So I'm going to pull out the sum from I equals 1 to n, and I'm going to have in parentheses my sum from j equals 1 to n of a j I, and that gets multiplied by pi I k. So I'm just changing the order of my sums here, and I'm noting that this sum over j's doesn't really depend on the values of the pi's. But now if I look and see what's in these parentheses here, what do I know about that sum? Oh, sum to 1. Yes, exactly. This has to be equal to 1 because this is the sum of column I in that matrix. And when we form that matrix A, we said we're going to normalize it so that every column sums to 1. And so then what we're left with here is simply the sum from I equals 1 to n of pi I k. So whatever my sum was at the kth iteration is going to be what my sum is at the jth iteration. And so at the k plus 1th iteration. And so if I initialize with a vector that sums to 1, a vector of probabilities, then all I need to do is at every iteration take that vector and multiply by a, no additional normalization, and at every iteration I will get a vector of probabilities that sums to 1. So this is a special way that we can do power iterations in the context of PageRank when we have Markov matrices. And so, for example, a common choice would be to set my first estimate to simply be a vector of 1s. So a vector that's n by 1 of 1s, and then I multiply that by 1 over n So I'm just saying I'm going to have uniform probability or uniform weight on every site in my network when I start off. And then I continue to iterate using these unnormalized power iterations with a Markov matrix in order to get this final vector of weights. Yes?
So when we initialize the pi, we must like have every term to like every term in pi to have a value, right? Because if we initialize pi maybe to be the like canonical vector, then like only one term would have like real multiple with a, and all the others would just be zero. We would not change.
So the question is, do we have to be careful about the initialization? Because what if we started off with an initial pi vector where some sites had no weight? We can get around that. I think that's not an issue because if you have no initial weight on site 1, for instance, but other sites do link to it, you will still visit that site even if it's not in that initial vector. But your question is getting at a bigger problem, which is imagine that I had a network, for instance, where I've got 2 different subnetworks that are not connected to one another, right? So if I start and I just do these power iterations, I'll only visit the network that's connected and I'll never visit the network that's disconnected from it. So there is sort of a fundamental issue with the way I've set this up because I have implicitly assumed that I can get to any site eventually as long as I hop around long enough. And that's not always the case, for instance, if we have these disconnected networks. So to resolve that issue, we introduce a damping factor. And in particular, what we're going to do is have this damping factor alpha, which is just a scalar that's somewhere between 0 and 1. And typically, for PageRank, alpha is 0.85. Seems to work well empirically. And then what we do is the following. We're going to change the way we do our random surfing. So we're going to basically flip a coin where probability of it coming up heads is alpha and the probability of it coming up tails is 1 minus alpha. And then based on that coin flip, we're going to do the following. So with probability, we're just going to follow a link from whatever page we're currently at. So if alpha was equal to 1, this would be exactly the method that I described to you before. Oh, I thought it was the microphone, but someone's drilling. Okay, so with probability, one minus alpha, we're just going to go to a random website. So in the context of our little toy example here, right, we start off at some site and we keep doing random surfing, but 15% of the time our coin is going to come up tails and we're just going to choose a random site. It might be in that same network, but it might be in a different subnetwork. And so we're going to allow ourselves to hop around totally at random, in this case, 15% of the time. Okay, so algorithmically that makes sense. Can we still use power iterations and eigen decompositions? And the answer is yes. So in particular, we can define a matrix, G, for Google, which is equal to, alpha times our matrix M plus 1 minus alpha times a normalized ones matrix. So I'm going to write this as 1 n by n. So this just means a matrix of ones that's n by n. And then I'm going to multiply that by the fraction 1 over n so that every column of this adds up to 1. Okay, so now I've got a new matrix that is representing the way that I am traversing the network with this new way of surfing, where with probability alpha, I'm going to follow a link using this matrix M. And with probability 1 minus alpha, I am going to just hop around randomly. And I apologize. I think here I want the matrix A. I know. And so now what we seek is a vector of importances pi that's going to be the leading eigenvector of my matrix G. So I can still use exactly the same concepts. I'm just introducing this little damping factor to account for the fact that this adjacency matrix might represent disconnected components of my network. Are there any questions? Yeah. So yeah, if you really wanted to like build a search engine, you would have to handle special cases like what if you get to a website that doesn't have any links? I mean, I guess it formally does fit within this framework in the sense that then you would just go to a random web page. But yeah, I mean, I think there are a number of ways in which the original algorithm can break down. You could get stuck in a loop where you just have sites that just linked only to each other, or you could have disconnected networks, or you could have random pages that don't link to anywhere else. And so this damping factor is designed to handle those edge cases. Yeah.
Also, you might have said this, but how does it decide which link to follow? Is it a follow or random?
Oh yeah, it's still just a random link. And it's uniformly at random, so it's not giving preference to any link over any other link. Yeah. Any other questions? Yeah.
So here for the yellow part here, I think that should be pi j of k plus 1, because we're already timing pi I k with the instead of just pi j k.
Oh, you're just saying here that should be k plus 1? Is that what you're saying? Okay, yes, thank you very much. All right, so in the lecture notes that will be posted online, I go into a more detailed explanation of why power iterations work, why this approach is going to lead you to actual eigenvectors. And so I do want to encourage you to look carefully at that explanation. It's a very kind of step-by-step and I think easy to follow explanation. But unless there are any other questions about PageRank, I want to move on to discussing ridge regression. Okay, so ridge regression is an extremely fundamental and important concept. In addition, if you've played around in the past with neural networks and you've used weight decay, it's intimately related to ridge regression. So we're going to learn some core ideas and concepts here, and we're going to focus on them in the context of least squares because that's where we are in the class right now. But a lot of the concepts that I'm introducing here and why they're important translate to other settings, including neural networks. And so hopefully this will be very broadly useful even as we initialize our discussion with a more narrow focus. Okay, so as we have before, we are going to be given training samples, xi and yi, where the xi's are our feature vectors. They are p-dimensional. Our yi's are just scalars. And we are going to have n different training samples, just like we've been doing with least squares. And as before, we could have our matrix of features X, where we could have X1 transpose as the first row, X2 transpose as the second row, Xn transpose as the nth row. So this matrix now is n by p. So recall that if X has p linearly independent columns, then we can find a unique least squares weight vector, W hat least squares, which was equal to X transpose X inverse X transpose Y. And we said if it didn't have p linearly independent columns, then this matrix here, X transpose X, was not full rank, and we could not compute its inverse. And so in order to make this work, we had to have the number of training samples be greater than the number of features, and the features be linearly independent. But there are many settings where those assumptions cannot be met. And so let's just think a little bit about what this looks like in the context of the singular value decomposition. And then ridge regression is going to allow us to sidestep some of these constraints that we have been having to deal with in the context of least squares. Okay, so as a warm-up, we're going to let X have a singular value decomposition, U sigma V transpose. So now what I can do is I can write my least squares solution, W hat LS, in terms of these matrices. So W hat least squares is going to be V sigma transpose U transpose, U sigma V transpose, inverse, times V sigma transpose U transpose times Y. So I'm just using the exact same formula, but I'm plugging in my SVD matrix. And now I'm going to start simplifying. So what's U transpose U? Identity, right? So that immediately goes away. And now I'm going to refer to sigma transpose times sigma. I'm just going to call that, for shorthand, sigma squared. So now what I have is V sigma squared, V transpose, inverse, times V sigma transpose, U transpose Y. Okay, now let's think about this thing that we're trying to invert here. So when I'm trying to invert a product of matrices like this, if each of the different factors are invertible, then what I can do is, similarly to what we do with the transpose, I can invert each of the factors and then change the order. So I can write this as V transpose inverse, sigma squared inverse, V inverse, V sigma transpose U transpose Y. So now I can do some additional simplifications. What's V inverse times V? Identity, great. And also, what's V transpose inverse? Okay, so just recall that for the SVD, V transpose V is equal to V transpose is equal to the identity matrix. So what this tells us then is that V transpose is equal to V inverse. And so in the context of the left side of the board here, if I have V transpose inverse, then this is V inverse inverse, which is just V. Okay, so this thing here is now just V. And so going up here, I can now write my least squares weight vector as simply being V times sigma, and I'm going to write sigma squared inverse as sigma to the negative 2, times sigma transpose U transpose Y. So now, first of all, let's remember that the rank of a matrix is equal to the number of non-zero singular values. So when we look at this from the perspective of the SVD, we can see that this only really works if there are no zeros in the diagonal of sigma. Or if I've got any zero-valued singular values, I'm not going to be able to compute this sigma inverse, right? So let me just flesh that out a little bit. Sigma to the negative 2 is going to be a diagonal matrix. I'm going to have 1 over sigma 1 squared, 1 over sigma 2 squared, all the way to 1 over sigma p squared. And everything else in the matrix is 0. So I can only really calculate this if none of these sigmas are equal to 0, right? As soon as one of them is equal to 0, then this blows up and it's not defined. And so when we required before that X transpose X was invertible, it's like saying all of those singular values had to be greater than 0. But once we do this, then if we were to look at sigma to the negative 2 times sigma transpose. So let's just remember sigma to the negative 2, that's going to be P by P. And sigma transpose is going to be P by N. And so we are going to have a matrix that looks like this. So we are going to have in the first diagonal the sigma 1 squared in the numerator, in the denominator, times a sigma 1 from that sigma transpose matrix. So we have sigma 1 over sigma 1 squared, or more simply, 1 over sigma 1. And then we've got 1 over sigma 2, all the way to 1 over sigma p. And then however many extra zeros are there to make it the right size. And so if we think about what's happening with this least squares solution, we're using our SVD basis matrices, U and V, and we're simply, so we take Y, we rotate it according to this U basis matrix, then we just multiply by a diagonal matrix corresponding to 1 over all the singular values, and then we rotate back into kind of weight space using this V matrix. So from here, hopefully it's clear. All of these singular values have to be greater than 0 for this to make any sense. But also, if some of the singular values are super close to 0, let's say 10 to the minus 6, right? 1 over 1,000,000. Then when we compute this matrix in the middle here, all of a sudden we're going to have some entries that are on the order of 1,000,000. So even if none of the singular values are 0, least squares can still lead us astray. And I'm going to show you a very specific example of that in a little bit. But ridge regression is designed to bypass this challenge, to bypass the issue that some of the sigmas might be 0, so we can't compute 1 over the sigmas at all. And some of them might just be not 0, but extremely close to 0. We're computing 1 over sigma gives us enormous numbers that can cause real problems with generalization. Okay. Okay. So with ridge regression, we're going to do something different than least squares. So I'm going to write W hat R for ridge. And this is going to be the argument W that minimizes the sum of squared errors, y minus xw, just like we did in least squares, plus another term. You're going to have lambda times the 2 norm of w. For some value of lambda that's greater than 0. Let's just say, for the sake of argument, like 0.1 or 0.01. This is something that a user would choose. It's a tuning parameter or a hyperparameter, and we'll talk more about it a little bit later. For now, imagine someone has told you a good value of lambda to use. So what we're doing here is we are saying we want to have a vector W that is a good predictor of the labels of all of our training samples, but also where the sum of the squares of the weights are not blowing up. We don't want to have any weights that are on the order of 1,000,000 if we can avoid it. Okay, so now let's think about, first of all, what the solution to this minimization problem looks like. And then we'll talk about how it relates to what we discussed with the SVD with least squares. Okay, so to solve this optimization problem, there are a couple of different techniques that we could use. So one is we could set gradients to 0. So in particular, I am going to call this whole thing my loss function, which is a function of W. And now what I want to know is what is the gradient of that loss with respect to W. So we talked about that gradient before for the first term here, for least squares. And there it looked like y minus xw times x transpose times 2. So that's what we calculated, times negative 2? Yeah, times negative 2. So this is what we calculated when we did it for just least squares. And then we do something analogous here. So we have negative 2 lambda times w. So we just have a little extra term on our gradient corresponding to this extra term in our loss function. And, sorry, not negative, positive. And just to be clear, because I might say it and I want to be explicit, I'm going to call this a regularizer. Or sometimes people will call it a regularization function. And so in this context, what we're doing is we're saying we want to promote weight vectors that are more regular than others. And by regular in this context, we mean that the sums of the squares of the entries are small when possible. Okay, so our gradient has an extra term in it corresponding to this regularization component of our loss function. And so now what we can do is set this equal to 0, which gives us that negative, positive 2 x transpose y is going to be equal to positive 2 x transpose x w plus 2 lambda w. And what I'm going to do to help with my next step is I'm going to just insert a little identity matrix there. The identity matrix doesn't change anything, but it is a nice square matrix that's the same size as x transpose x. And that's going to help me simplify things. So first of all, I'm just going to cancel out all my 2's. They're not doing anything for me. And then I'm going to simplify the right-hand side of my equation here, where what I want to do is I want to pull out the w and have everything that gets multiplied by w on the left part here in parentheses. So I'm going to have x transpose x plus lambda times an identity. And so now if I want to solve for w, I get that w hat with ridged regression just corresponds to x transpose x plus lambda identity inverse times x transpose y. So in the special case where lambda is equal to 0, then this looks exactly like least squares, and this looks exactly like the least squares weight vector. It's only when lambda is greater than 0 that we're doing something different here. And the key point that I'm going to illustrate to you is that there are going to be times when x transpose x is not invertible, where we cannot do least squares, like I mentioned. But x transpose x plus lambda identity is always invertible. So I can always compute this ridge regression estimate. So ridge regression is going to be possible even when least squares is not possible. And it's going to help us avoid overfitting. And I'll describe how that works as well. Are there any questions so far? Okay. So just like before, there is another way that you can compute this ridge regression estimate, and I think it might be just useful to walk through it really quickly. So the other way we could do it is just massage it to look like least squares. So in particular, I could take my loss function and I could write it as my squared error, y minus xw, 2 norm squared, plus lambda. But now instead of just writing w, I can write this as 0 minus identity w. It's exactly the same, but now what I can do is I can rewrite this in a way that will let me use standard least squares. So in particular, this is exactly the same as concatenating my y vector and my 0 vector and subtracting from it my x matrix concatenated with my lambda identity matrix times w, square root of lambda. Yes, square root of lambda, 2 norm squared. So what I can do is I can call this y tilde, and I can call this x tilde, so that what this is simply the 2 norm squared of y tilde minus x tilde w. And so then I can compute from here that my w hat for ridge regression would correspond to x tilde transpose x tilde inverse x tilde transpose y tilde. And then I can just plug in my definitions of x tilde and y tilde to get the same expression as we had over on the left. Okay, so nothing we're doing here is a big shift in terms of the mathematics and the linear algebra from what we've already been doing. The shift is coming from what's happening with the singular values and what that means for generalization and bypassing some of the limitations of least squares. Okay, so in particular, we said that w hat ridge is going to look like x transpose x plus lambda identity inverse x transpose y. And now what I'm going to do, just like we did with least squares, is rewrite this using the singular value decomposition. So I'm going to have v sigma squared v transpose plus lambda identity inverse v transpose sigma transpose, or I'm sorry, I think that was a v sigma transpose u transpose y. Okay, so we're just using the same techniques as we used before when we started thinking about least squares in the context of the SVD, only now we've got this little extra lambda identity in here. Now remember, with the SVD, we can write this I matrix as VV transpose. And so I can rewrite this as V sigma squared V transpose plus V lambda I V transpose inverse V sigma transpose U transpose Y. And once I've written it like this, I haven't really changed anything, but now I can group the two terms inside of my parentheses here to rewrite this as V sigma squared plus lambda identity V transpose inverse V sigma transpose U transpose Y. And now I can do the same steps as we did with least squares when I'm taking this inverse so that I get V sigma squared plus lambda identity inverse sigma transpose U transpose Y. Okay, so this here is my vector of ridge regression weights in terms of my ridge regression penalty factor lambda and in terms of the SVD matrices of my feature matrix X. So if you remember when we were talking about least squares, we said we would run into trouble if sigma had some zero valued singular values, because this product sigma to the negative 2 times sigma transpose looked like 1 over sigma 1, 1 over sigma 2, etc. As soon as one of those is 0, things blow up. But now over here, when we think about what we're actually inverting, we're inverting sigma squared plus lambda identity. Lambda is greater than 0. So all the diagonal entries of this matrix are going to be greater than 0. So let me just be a little bit more explicit. If we look at sigma squared plus lambda identity inverse, then what we get is in this top entry, 1 over sigma 1 squared plus lambda. And then we have 1 over sigma 2 squared plus lambda, all the way down to 1 over sigma p squared plus lambda. And so since lambda is greater than 0, no matter how small these singular values are, even if they're equal to 0, I'm never actually dividing by 0 here. And so when I look at sigma squared plus lambda identity inverse times sigma transpose, the thing that's showing up here in the middle of my ridge regression estimator, what I'm getting is a matrix that looks like sigma 1 over sigma 1 squared plus lambda, sigma 2 over sigma 2 squared plus lambda, all the way down to sigma p over sigma p squared plus lambda. And then this might be a different size, so we might have some additional 0 valued columns to tack on. So never do we have to worry about dividing by 0 in this expression for ridge regression. So the role of, when we talked about ridge regression, what we said was we started off by saying, well, we want to ensure that whatever weight vector we choose does not have huge values if we can avoid it. We want to penalize vectors W that have really giant factors. And if there are many different W's that give reasonably good predictions on our training data, then we prefer to choose the one that has the smallest norm. So we had that sort of hand-wavy explanation of what's happening here. And now what we have through the singular value decomposition is another understanding of what's happening. So basically what's happening is we are tempering the singular values that show up in this expression. So if we were to think about the least squares expression, some of the singular values could be close to 0, and we would have, and so if we didn't have lambda here, we could be dividing by 0 or dividing by extremely small numbers. But now because of the lambda, we're never dividing by 0. And in fact, the thing that we divide by is never going to be smaller than lambda. Okay, so another way of saying this, I just want to write it out explicitly because it's a super important point. X transpose X may not be invertible. But X transpose X plus lambda identity for some lambda that's greater than 0 is always invertible. And so we can always compute the ridge regression solution, even if we don't have linearly independent features, even if we've got more features than we have samples, all the things that we were worried about before, we can handle now because of this ridge regression penalty. Okay, so now I want to talk about ridge regression and overfitting. So let's imagine that I get a bunch of points, a bunch of training samples. So my horizontal axis is X, vertical axis are my labels Y, and now I'm going to plot them, and they look something like this. And now imagine that I try 2 different ways to fit these samples by using the same kind of polynomial fitting idea that we talked about earlier in the quarter, where we formed a Vandermonde matrix in order to do least squares. So if I let my polynomial order be really high, I let myself have really big polynomial coefficients for really high order polynomials, then I could maybe even fit this data exactly. But it can just be extremely, maybe I'll just be a little bit more exaggerated here, right? If I'm like constraining myself to polynomials, like it can just be exaggerated. And based on these orange dots, you might not think that this is the most likely or reasonable predictor of what's happening, say, when X is equal to 0, right? Every single training sample here is up here with positive Y's. And because I've fit this high order polynomial and tried to match my training data exactly, then my predictor is saying, oh, you should, when X is 0, predict a label of, say, -10. And so what you might prefer conceptually is a smooth, lower order polynomial that's close to fitting the data, that doesn't perfectly fit the data, but we might expect to be able to perform better and give more reasonable estimates on new samples later on when we deploy our model. And so if I were to force myself to use high order polynomials and only do least squares, and I try to fit my data as close as I can, I risk running into this green scenario where I have something that's really fit to the training data very accurately, but may not perform well on my test data. Whereas with ridge regression, I am promoting solutions that are more regular or smoother in this case, that hopefully are going to give me better performance on my test data and better generalization. Okay, so this is a very hand-wavy claim, but we can actually see it in a very concrete setting. So what we're going to contrast is the following. So with least squares, we have sigma to the -2 times sigma transpose that shows up within our least squares estimator. And we said that looks like 1 over sigma 1, 1 over sigma 2, all the way to 1 over sigma p. And then if we were to do ridge, we would have sigma squared plus lambda identity inverse times sigma transpose. And that looks like sigma 1 over sigma 1 squared plus lambda, sigma 2 over sigma 2 squared plus lambda, all the way to sigma p over sigma p squared plus lambda. Okay, now let's imagine that the way my labels y are generated is by taking this x that corresponds to my training features and multiplying by some true weight vector w star, but then just adding a little bit of noise or error to those labels. So there is a true weight vector that generated my labels, but all those labels have just been corrupted by a little bit of error or measurement noise. Okay. We also are going to imagine that x has some small singular values. So, for instance, let's imagine that sigma p is not equal to 0. So we've said, all right, least squares is a valid approach when none of the singular values are equal to 0. But let's imagine that sigma p is like 10 to the minus 6. Okay? So we're still within the realm of what we said is allowable for least squares. And now what we're going to do is we're going to examine in this setting what happens if we do least squares and how that's different from what happens if we do ridge. Okay, now over here, before I erase, I'm going to jump back a little bit and just mention this regularizer that I'm describing here, 1 times the sum of the squares of all of my weights or all my parameters. This in the neural network community is called weight decay. So everything, when we talk about ridge, regression, we're really talking about this weight decay regularization plus least squares. When people talk more generally about weight decay, they might not be using a least squares loss function explicitly. They might be using something else, but the regularizer is still the sum of the squares of all the weights or the parameters we're trying to learn. Okay, so just a little vocabulary. Okay, so first of all, I want to say that with ridge, when we look at these diagonal terms, let's just choose the ith one. So we've got sigma I over sigma I squared plus lambda. So we can think about what that value will be in a couple of different cases of interest. So we might be interested in settings where the singular values are large, maybe much larger than lambda. So in that case, this is going to look close to, maybe let's put an approximation here, 1 over sigma I. So when the sigma i's are big, when we've got large singular values, then the lambda is going to play a very small role. And this is going to look a lot like the corresponding diagonal value that we have with least squares. But when sigma I is close to 0, then we would have something that looks like 0 over 0 plus lambda. We're going to get something that's close to 0. So what this is telling us is happening is whenever we've got large singular values, the lambda is not going to play a huge role. We're going to be behaving like least squares would behave. And wherever we have small singular values, we're going to avoid having anything blow up. And in fact, we'll just say that this ratio is going to be close to 0. Okay, so that's the effect of it. And I'm afraid I've lost a page. Okay. So going back to our example with a little bit of measurement noise. If we were to look at W hat least squares, we've got X transpose X inverse X transpose, and then normally I would write Y here, but instead what I'm going to write is X W star plus this noise epsilon. And so now I can rewrite this. I can have X transpose X inverse, X transpose X W star, plus X transpose X inverse, X transpose epsilon. So here, I've got X transpose X inverse times X transpose X. Those cancel out. And so what I have is W star. This is good. We really want our least squares estimate to be as close as possible to W star. But then we've added on to this thing here, X transpose X inverse, X transpose epsilon. And if we think about what's happening here in terms of the SVD, right, what we're going to get is this V sigma to the -2 sigma transpose U transpose epsilon. And so when one of the singular values is close to 0, say sigma p is 10 to the -6, then this is going to have an entry that's close to 10 to the 6, close to 1,000,000. So if we think about what's happening here, we're taking our noise, we're rotating it into this U space, but that doesn't change how big it is, it's just a rotation. Then we're multiplying by 1,000,000 and then rotating again. So what we have is the true thing that we care about, plus our noise that's been amplified potentially by a factor of 1,000,000. And so what you see is honestly garbage in many settings because this is so small compared to our measurement noise amplified by a factor of 1,000,000. Okay, so then that means that we've got a very noisy, inaccurate least squares estimate. And if we try to make predictions on new data, this is really going to dominate and give us bad predictions on new data. In contrast, this will only take a minute. With ridge, we have that W hat ridge is equal to X transpose X plus lambda identity inverse X transpose. And now again, I'm going to put in XW star plus my epsilon. And so I'm going to get X transpose X plus lambda identity inverse X transpose XW star plus X transpose X lambda identity inverse X transpose epsilon. So when I look at this now, for the first term, the thing that I'm multiplying by X transpose X is no longer exactly X transpose X inverse. It's been perturbed a little bit by this lambda. But if lambda is small, then these two factors will be close to canceling themselves out or each other out. And so this will be not exactly, but it'll be close to W star. So we've got a little bit of error now that we're introducing through this lambda here. It's not going to be exactly lambda star. But we're going to make up for that small error by this being much better. Because now, when we think about what's happening here, this is equal to, we said, V sigma squared plus lambda identity inverse sigma transpose U transpose epsilon. So now we're taking our noise, rotating into the U space like we talked about before. But now we are no longer multiplying by 1,000,000, right? Because we're no longer dividing anything by 10 to the -6. The lambda is tempering that. And so we're not going to take whatever that noise is and multiply it by this factor of 1,000,000. And instead, we'll be multiplying it by something that's much smaller because of the presence of that lambda. And so this will not blow up the same way. And so what we will have is a slightly erroneous estimate of W star plus some noise that's not too huge. And overall, the combination of those two things is much closer to W star than what we got when we were just doing least squares over here, over somewhere. I lost it here. Then what we got over here, where we didn't have that sort of bias on W star, we didn't have any error in that first term, but the second term was so huge that we lost sight of how good the first term was. Okay, we'll continue to talk about ridge regression on Thursday. Thank you very much, and have a good couple of days.